Sure. Good afternoon, everyone. It is my great pleasure that Bartłomiej Kielak, who is visiting our group for a couple of months, agreed to give a seminar about one of his recent results of curves on torus with few intersections. And yes, Bartek will tell us more.
Yeah, thank you very much for the invitation and this nice introduction. So the thing I'd like to talk about is joint work with Igor Balla, Marek Filakovský, Král, and Niklas Schlomberg. And actually, all of us, apart from Niklas, used to be affiliated with Masaryk University just a while ago. But as you can see, things changed slightly over the course of the last few months. So let me move to the title, because there are quite a few keywords in here that perhaps need some more explanation. So curves and torus, or more general, curves on surfaces. So when I say about curves, I always think about simple curves, which means they have no self-intersections, and about closed curves, so we basically have loops somehow convoluted around some surface like a torus. So here's an example in the picture. And when we talk about torus, then actually it's good to think about it as a quotient space, like a real plane where points are identified if its coordinates are the same modulo 1. So the main object of study for topologists is something which we call K-system. And we say that a set of curves on some given surface sigma is a K-system if any two curves from our set are non-homotopic and any two of them intersect at most K points. So now the thing is, you can easily imagine plenty of curves on a torus such that none of them have actually intersections with each other. But the point is, if two curves have no intersections on a torus, then they are actually homotopic to each other. So you can have infinitely many curves. You just take one curve, like very simple one, and you just rotate it around the torus. So you can have infinitely many, but they will be all basically the same thing. So in order to make things slightly more interesting, we need to impose some criterion of them being distinct in some sense. And there is also another question, why actually should we care about this kind of results? And one of the motivations, let me maybe also introduce that we are interested in the maximum size of such K-systems. By one of the motivations by people who actually proved some first results about these things, like Ivan Manic and Mohar in '96, is that they wanted to apply it to some graphs on surfaces to get some results on some properties of them. Maybe I will not name any of them because this is kind of requires a bit of definitions, which I'm not familiar with. But let's just focus on the fact that they prove that for any compact surface, this number is always finite. So in particular, it is finite for a torus, which we're mostly interested with. And torus has also this very nice property that it is a very simple structure, a very simple surface, and many things on torus are simply much simpler. Okay, maybe I use some words too much, but let me maybe explain what I mean. So for instance, the homotopy classes, because I said that we only want to consider non-homotopic curves. But how do we actually can say that two curves are non-homotopic? Where it turns out that each homotopy class can be described just by a pair of integers, mn, such that both of them are coprime. This coprime condition is just to ensure that the curve that we would like to think about has no self-intersections. And such a pair of integers corresponds to some parametrization of a curve, which is given by this CMN, which just multiply first coordinate by m and the second coordinate by n. So here's an example on a picture. So remember that we think of a torus as a plane where points are identified. So this is an actual picture of some curve. And also note that if I have two pairs like mn and minus m minus n, they both correspond to the same homotopy class. And you can see it if you realize that actually we can attach this curve, because right now this segment is attached at something which we would call origin, but it can be attached at any different point, because all integer points are the same point on our torus, because we have this identification. Okay, so let's take two curves. So once we understand what does it mean for two curves to be non-homotopic, and we have some nice examples of representatives of the homotopic classes, then how to determine the number of intersection points between them. And once again, it turns out that it is very straightforward. We just have those two pairs of integers, and we just compute something which basically looks like a determinant of some matrix given by those two vectors. So it's pretty cool, but the question is why this number has something to do with the number of intersections of those two curves. And just to give you some intuition, recall that we're working on integer points in our real plane, and if we have some polygon which is defined by such integer points, then we also have Pick's theorem, which says that the area of such a polygon is given by the number of points which are inside our polygon, plus the half of points which are at the boundary, and -1. But what is the point? We only consider pairs of points m and n, which are coprime. So we know what is the number of points on the boundary. It's always 4. So we only have the external vertices, like the corners. So if we make it, if we halve it, then we get 2. If we subtract 1, we just get 1. So basically, the area of our polygon, or the number of intersections, should be the number of interior points plus 1. So what is remaining is to understand what is how we can pair those internal points with intersections. And it is actually very straightforward. We just need to reattach our curve to a different integer point inside our parallelogram in this case. And note that for each different attachment, I actually draw the same curve because remember, all integer points are the same on the torus, but all these points are different, so we identify different intersection points. And because we have 24 points inside, and we can choose whichever corner we want for the last point, we can identify all 25 intersection points in this example. But this is just to give you an idea where this number comes from. What actually is important for us is simply that if we have two pairs of integers which correspond to homotopic classes, then we just have a ready formula to compute the number of intersections. Great. So let me oh, by the way, if you have some questions, then please simply interrupt me. So let me discuss the results about the maximum number of curves on torus, like the maximum size of K-systems. So first theorem is also due to Jovan, Malnic, and Mohar, who determined that in the special case of a torus, we can actually give some linear bounds in terms of K. So we have at least K plus 1 in a maximal K-system, but no more than 2K plus 3. A few years later, it was observed by Ago that if we consider some clever counting modulo P, then we can actually derive that the maximum size of a K-system on a torus is no larger than 1 plus the smallest prime number, which is larger than K. And what is the smallest prime number larger than K? So we basically ask about the gaps between prime numbers on integers. So we do have a few results about this. And one of the best results is due to Baker, Harman, and Pins from 2001, which gives us that the number of the maximum size of a K-system is at most K plus something which is roughly square root of K. But we also have some old result by Kramer from 1921 that if we believe in Riemann hypothesis, then we can actually narrow the gaps between prime numbers. And this way we can obtain an upper bound of K plus big of square root of K. This upper bound was actually verified just 2 years ago by Aougab and Gaster. Of course, they didn't rely on Riemann hypothesis. Instead, they just came up with some elementary idea, but still it involved working in some hyperbolic space. They considered some horoballs, like packing horoballs, and this is something I have very little knowledge about, so I will not talk more about this approach. And instead, I will just proceed to our result, which is that we actually determined the optimum maximum size of any k-nice set on a torus. Like for every k, we know what is the maximum possible. And in particular, this maximum is never larger than k plus 6. This k plus 6 can be achieved only for 4 values of k. K plus 5 can be achieved only for 13 values of k. And apart from a special set of 59 values of k, we have just a very nice formula how it looks like, which is just given below. So the remainder of my talk will be just to discuss how we came up with this result, what were like the main ideas. Let me start with the reformulation of the problem, because instead of working in topology, we would rather want to work with some integers. Integers are nice, and so we introduce the notion of a k-nice set. So we say that a set of pairs of integers is k-nice if for every point from this set, its coordinates are coprime, and also if I include some point, then the minus point is not included. And finally, we have third condition, which you can probably recognize as this intersection criterion. So if I take two different points, then they correspond to some curves in my K system, so they shouldn't have too many crossings, like too many intersections. So basically, those criterions are just the translation of what we said so far about curves on torus. But just now we are just talking about integers and divisibility. So in particular, the largest size of a K system on a torus is just the largest size of a k-nice set in our setting. So let me give some example. So this is one of the simplest examples. And you can notice that I take one point which is at level 0. And when I say level 0, I mean that the second coordinate is equal to 0. And all the remaining points are at level 1. So I basically just have points on 2 levels. There are in total k plus 2 points in this example. And it is pretty straightforward to see that this is indeed a k-nice set. So we can do slightly better if we involve level 2. We can actually take the previous example and put one additional point, k2 specifically. But this construction only works if k is not divisible by 2, which is for obvious reason that k and 2 have to be coprime. And if we involve level 3, then we can do actually something even better. We can achieve a k-nice set of size k plus 4, but here it is somewhat more convoluted. I mean, we have some weirder criterion on k. It has to be congruent to 2 modulo 6. So it is no longer so obvious that we actually get something which is k-nice. But it works. And it is also a good moment to introduce one crucial notion of this talk, which is height of a set. And it is just the maximum level up to absolute value that is involved in our construction. So in particular, here we considered k-nice sets of height 1, 2, and 3 respectively. And this is basically the best what we can do if we consider k-nice sets of height at most 3. So this lemma can be proven using elementary approach, but it is actually pretty messy because you need to consider many different cases. Like this k congruent to 2 modulo 6 should give you an idea that something is really going on, and you need to be really careful when doing any considerations here. But what happens if the height is larger? Because on one side, if you allow points which are higher, then you have more freedom, more possibility to create k-nice sets. But as it will turn out, having a point which is high is actually not beneficial in the long run for the size of our k-nice set. And the main reason is the intersection criterion, because this intersection criterion is basically saying that if I have some point in my set, then it defines 2 lines, And those two lines say that all of the other points in our set have to be between those two lines. And the higher I take my point, then actually the narrower, the more strict those lines become. Okay, so let's move on. And one of the most important things to do at the beginning is to find some reasonable upper bound on the height that is enough to consider in our problem. And let me introduce some notion. So if I take some matrix A of integer matrix, then I can define a transformation of some set. It may be k-nice, it doesn't have to be, simply by applying this matrix to any point from this set. And we say that two sets are actually equivalent if one can be obtained from the other by applying some unimodular matrix, which means that it has integer coefficients and its determinant is plus minus 1. In particular, unimodular matrices have inverses, which are also unimodular. So this is indeed an equivalence relation of on sets. And what you can expect is the following lemma, that if I have some q-nice set, then this property of being k-nice is preserved by applying unimodular matrices. And what is the reason? I mean, let me just give a few words of explanation. So imagine that we obtained some point ax, which coordinates are not coprime, so they are divisible by x. But then if I apply anything to this point, to those coordinates, then I have like any matrix, then basically I obtain a new point which coordinates are linear combinations of the original. So both coordinates are divisible by s again. But in particular, I can apply the inverse of A, which is unimodular, and I get my original point, which basically says that the property of points being coprime is preserved when applying unimodular matrices. Also, we need to ensure that if I have a point x in my new set, then minus x is not included, or y and minus y. But this is again basic because unimodular matrices have only unique solutions, because those are like equations that we want to solve, because the determinant is positive. And finally, we need to verify that the intersection criterion is preserved. But this is pretty natural if you think about this matrix A as some actual transformation of the torus. And this transformation is also invertible, and such a transformation and linear, so it shouldn't create any new intersections, or actually it should preserve the number of intersections between two curves. But you can also verify it more directly by just looking at some basic linear algebra identities. Okay, so once we know the notion of equivalent sets, so let me define the lemma that any k-nice set Q is equivalent to some k-nice set of height at most square root of 2k. And what is the idea of the proof? So first, I want to take the point which is at maximum level. It has some x coordinate, and now I would like to move this point as close to 0, like this, the first coordinate, as close to 0 as possible. And it can be achieved by applying some specific matrix, which is given on the slide. But this matrix allows me only to move this point by multiples of the second coordinate, which is y. And therefore, I can move this point to 0 only as close as half of the second coordinate, which is h divided by 2. So this is the first step. And now we have this intersection criterion, which says that it has to be preserved after this transformation, because this is how equivalence works for k-nice sets. But what follows? If by any chance our set after the transformation is of large height, I mean it's of the same height as the original, then it would turn out that for this arbitrarily chosen point, its first coordinate would be small, would be at most square root of 2k, and it's just a matter of some triangle inequality, basically. But if I have a set which is narrow, then I can actually just flip the coordinates to make it instead of low height. I just flip the coordinates, and of course it can be achieved by some unimodular matrix. So that's the proof. And now, two more useful notions. So we say that my k-nice set Q is x non-negative if first coordinate of every point is non-negative, and we say that it is y non-negative if every second coordinate of any point is non-negative. So we can actually summarize things and say that if I take any k-nice set Q, then I can actually replace it with another set which is of the same size, which is k-nice, which is both x and y non-negative, and which is also of reasonably low height, which is at most square root of 2k. And how to do it? First, we can guarantee that it is of low height because of the previous lemma. Then we can guarantee that it is actually y non-negative, and we can simply do this by replacing some point mn by its negative version, minus m minus n, because those points correspond to the same curve, basically. And finally, we apply some transformation, which means we move all the points to the right. And now we actually move all points to the right because we move them by some multiple of the second coordinate, but now second coordinate is always positive for all the points in our set. So once we choose some suitable value of m in this transformation, we obtain a set which has all desired properties. So actually, from this point of the talk, we can always think that if I take some k-nice set, then it has all three properties that are listed on this slide.
I have a stupid question.
Yes?
Why y cannot be 0 for one of the points?
It can be 0, but what is the problem?
I don't understand the shift.
Okay. But we can only have one point with this property.
Okay.
Because its x coordinate is either plus or minus 1. Because we have this coprime condition.
Okay.
And once you have this point, you can basically replace it with plus 1, 0.
All right. Okay. I see.
So yeah, but that's a good point. We should do it at the end, probably. So once we know that we can work with subsets, then let me formulate the first bold theorem of this talk, which says that if I consider a k-nice set of large height, and here large means larger than 41,020, then we can actually get a reasonable upper bound on the size of this set. I mean, I call it reasonable, even though it looks kind of mysterious. But let me show this. Let me show you this, that this coefficient, which is next to k, is actually strictly smaller than 1. And remember also that the height is of order square root of k. So the height is small, and this coefficient next to h is also small, and it's like deterministic. So in particular, it implies that if I consider large k-nice sets with large height, then they definitely have to be small. So like this is like an essential step of our proof, because this way we will be able later to focus on sets with height which is bounded from above by some number. It will be reasonably large, but we will do something about it later. So what are the main ideas behind this proof? So first, in order to talk about the size of our set Q, I would like to define, I would like to say what happens at the levels, particular levels. So the set Qi consists of those numbers, like the first coordinate of points, which are at the level I. And we also would like to introduce something which would be an estimation of the length of this interval, I mean, interval defined by points. But remember that in principle, we can have 0 points on a level I. So then taking maximum and minimum makes no sense. But instead of saying that we take here 0, we would like to do something which may be not really clear why we want to do this instead. But still, we would like to consider the convex hull of our set. So we have some points, a finite number of points. We take convex hull of them, and then we look what happens at some level I. So now we always get some segment, and it has some length, and this length is just equal to Li.
It doesn't have to be an integer, right?
Yeah, it no longer has to be an integer. but it's not really relevant to us at this moment. But still, we can write this, that the size of Q is just the sum of Qi, like the sum of number of points which are at ith level, and each Qi can be estimated by Li plus 1. Which of course is very weak bound. Perhaps some level is empty and we take plenty of points instead, kind of. But the main reason behind it is that Li's have they behave very nicely, and I will explain later what do I mean that they behave nicely. Like they are much more predictable in a sense. But okay. When we replace the size of Qi by the length of the interval, then we definitely take too much. Because remember that at the level I, we only have points which are coprime to I. And what does it mean that we are coprime to I? It means that we are coprime to any prime divisor of I. And now, in order to understand this rho I, we can think about this process of sampling a random integer from some fixed interval. So what is the probability that I sample something which is coprime to some prime number p? It is basically 1 minus 1 over p, or at least it is something which should be of this order, at least for some specific length of our interval. So let's assume the ideal situation that this interval is of correct length. And now we want to perform the same sampling for different values of p. So I would like to sample points which is coprime to some different prime number. And now realize that in a nice scenario, all of those events being coprime to different primes are actually independent. And the probability of independent events is just the product of those probabilities. And this is exactly the definition of rho I. So in the end, we would expect to find rho I times length of this segment at level I of points in Qi. Like this would be our desired upper bound. But of course, I was talking that so far I was only considering the ideal situation. So we need to take some minor correction because we can expect some kind of error if the length of interval is not ideal. But fortunately, this error can be computed. And it can be computed, I define it as alpha I. I mean, there is some specific formula for it, but it can be done by computer, and it's basically nothing that should worry us too much. But thanks to that, we are able to write that the size of Qi is at most this error alpha I plus the length of the interval times this probability, rho I. So the size of Q is just the sum of those things. But what is the problem? The problem with this sum is that those alpha i's are kind of unpredictable. Alpha i's and rho i's, they are as unpredictable as the prime numbers are. So in order to make things more structured, we can actually focus only on some divisors of i's. Instead of taking all prime divisors, we only take those which are from the set 2, 3, 5, or 7. So for instance, now prime divisors of 125, okay, it's just 5. It has only one prime divisor, it is 5. And now prime divisors of 666, so P is 66, would be now just 6 because it has 3 prime divisors, 2, 3, and 11, but we only care about 2 of them. We care about 2 and 3. And finally, the prime divisor of 29 from our perspective would be just 1. So we basically take all of the points from our segment if we take P of some prime number, which is large. So you can see that actually we can potentially lose quite a lot if we try to replace i's with P of i's. But on the other hand, this sequence of P of i's is now periodic. And it's periodic with period of 210 because it only depends on primes 2, 3, 5, 5, and 7. Oh, and also I should have mentioned it like this, that I can just replace i's with pi's when I estimate the size of set Qi. So for I equal to 29, I definitely lose a lot. but the intuition is that most of the points are actually sitting at the bottom. So even though I may potentially get some weaker bound for the higher levels, I don't expect too many points to be at the higher levels. And so we can just rewrite things, group things together. And in particular, if I look at the row i's, then I can just take the sum over all possible values of from 1 to 210. This is like the second part of the sum. So I group the li's according to the value of row something. And there is also the sum of these coefficients. But right now, these things are periodic because pi's are periodic. And because they are periodic, they are definitely bounded by h times something. But since we have computer can compute all of the coefficients, we can actually get as exact bound as possible. So this is like where this coefficient from the theorem comes from, like this 4,000 something times h. And there is still one question. Oh yeah, I don't have too much time. What to do about this sum of li's? And note that so far I didn't use at all the properties of li's. They were just some numbers, and I was doing some computations. So let us actually involve them. And note that since our set Q, like the convex pool of Q, is now a convex set, then the levels form a very nice sequence of numbers. I mean, this sequence is first increasing because the levels increase, and then they start to decrease. I think there is some notion of unimodal sequence which satisfies this kind of property. And we also define M to be the maximum length of a level, of a segment at some level. And once we use these properties, we can actually bound this sum. Oh, maybe I didn't mention that, but we group them according to indices which are congruent to A modulo 210. So this is the way how we group those layers. And no matter what is this value of A, we can always bound it by the length, somehow by the length of the longest segment in our section, and something which is corresponding to the area of our convex hull. So the remaining questions are if you can do something about the longest layer and about the area. And so we have two lemmas. I will just state them without proving, but at least the first one I think is kind of intuitive. That if I have some finite set of points, here I maybe don't assume finiteness, but it is enough to assume finiteness. And for any 2 points of them, this crossing criterion is satisfied. Then when you take the convex hull, this crossing criterion would also remain satisfied for all the points from the convex hull of S. And we apply it. So in particular, the convex hull of RQ satisfies this crossing criterion. And now the second lemma says that if I have such a nice convex set, which is Y non-negative, and it satisfies this crossing criterion with this constant K, then we actually have a very nice bound on the area of this set, which is at most pi times K over 2. And this is exactly where pi comes from in the original statement of the theorem. And you can also guess that this lemma has this geometric nature. So in fact, we apply here some reasoning from geometry. We compute some integrals to get this bound. So once we apply it, we can just replace area by this value from the lemma. And also using the same lemma, we can find some nice upper bound on the length of this longest thing, longest interval in our convex hull, and we get some numbers. And if we put them together, then in the end, we would obtain exactly what we wanted in the main statement of the theorem. And I think that's it, what I wanted to say about this theorem. So let me briefly discuss what happens next, because now we know that we can restrict our attention only to sets which have some fixed height, which is kind of small, but maybe not too much. So recall that we have this bound, which is actually true in general on the number of points at level I. And now I would like to write this length Li as the difference of endpoints. So I define this sigma I and tau I as the minimum and max of this segment at level I when I take the convex hull. And also I want to define some beta H, which is essentially just take anything which is not related to Li and just put it together. And this way I can write that the size of Q is at most sum of everything which is not related to Li plus rho I times Li, but Li I can rewrite as the difference of the endpoints. And so what is the reason for me to actually rewrite Li's in terms of difference of the things? And basically, it's because I would like to find an upper bound for this quantity. And note that this quantity actually, okay, in principle, it depends on H and on K. So that's why in the formulation of this linear program, I have also K, which exists in the condition, in the crossing condition. And also note that we need to verify this crossing condition only for the extremal points, so for the endpoints of the segments. So that's why we need those sigma i's and tau i's. But on the other hand, everything here is linear, so I can basically divide everything by k, and now I get a linear program which depends only on h. And I can try to basically solve it. And this objective value I can denote by gamma h, and then I can just plug into the formula. And also note that this beta h is also something which depends only on h. It doesn't depend on k. It doesn't depend on the set q that we consider. So it is also something which can we compute directly by using computer, for instance. So the question is, what is the maximum value of gamma h? So we would like it to be strictly smaller than 1, because then we get that this size of q could be actually smaller than k plus 3, for instance. This is like our ultimate goal, to say that the size of q cannot be too large. And that's indeed the case. So for this linear program, if h is actually equal to 1, 2, or 3, then the optimal value is equal to 1, which should not be surprising because we actually have the solutions. We presented it at the beginning of the lecture, that this gamma should be equal to 1. But otherwise, if h is larger than 3, then the optimal solution, like the maximum gamma, the value of gamma is strictly smaller than 1. And we get an immediate corollary from this, that if k is sufficiently large, then basically we need to have the size of a k-nice set at most k plus 4. And if we are more careful and we try to look exactly at the estimates that we got, then we can derive this kind of result, that if we take k at least 3225, then actually we know everything what happens. So let's go one step further. I think I have still 3 minutes. So what can we do about k at most 3224? So recall that we had some lemma about bounding the height of a k-nice set, which is actually nice. It was very crucial for all of our proofs. But there is one problem with it. It is actually a bottleneck. So it is very weak, and in practice, we can usually find some equivalent set which has height even lower than the square root of 2k. So the question is, how much can we improve this lemma? And this is what we actually obtained. So if we consider k up to 3224, then we can replace any q-nice set with another one, any k-nice set with another one which has height at most square root of 4k divided by 3. And basically the proof goes almost the same way as before. So we fix some point, we move it to 0, then we look at some different point, and we assume that there exists some point which is actually very far away from 0, and the first coordinate is far away from 0. And the question is, what can we do in this case? So we can hope that maybe we can do some different modification to our set Q, find some different matrix, find different transform that would actually make our set small, like of small height or of small width. And we check that it actually happens always. And we did it just by computer verification. So in order to do this computer verification, we had to check all possible choices of my point at the top and also of my point, which is far away from 0. But it is doable and it actually works pretty nicely. And this allows us to bring the value of k down to 1892, which gives a last question, what actually do with those guys? So how to determine the maximum size of a k-nice set if k is at most 1891? And now we apply the simplest solution possible. We just consider all possible k-nice sets, which maybe sounds ridiculous, but of course we don't do it ourselves. We just run some computer program. And again, if you are careful and we realize that we don't have to consider super all of them, but we can actually restrict our attention to those which satisfy some certain conditions, then we can actually do this computer search in a finite time, like a couple of hours or maybe days. But it is doable. And I think that's all that I wanted to say.
Thank you very much, Bartek, for a really cool talk. Any questions?
So there is nothing left open around this problem?
Yes, so for torus, I think there is nothing left. But in principle, I said that the topologists were interested in what happens for an arbitrary surface. So torus was nice because it has a very nice interpretation in terms of pairs of integers and everything. So I think something similar may be done for some more complex surfaces, but it is not exactly as simple as we would like it to be. I think it gets really messy very quickly. I mean, so far we didn't try anything else, and it's mostly to the fact that, I mean, we would be basically in a completely different situations, and most of the tools that we applied here will be really hard to translate to other settings. Yeah, I mean, it all relates to, like, for instance, what is the number of intersections between two curves from different homotopic classes? I think there is some formula, like there is some description of homotopic classes and some formula which describes what is the number of crossings, but it is no longer as simple as it was in a single torus case. And in fact, I mean, there was some line of research for general surfaces, and the only result I recall is some upper bound, I think it was by Przetycki, who fixed some genus G. No, sorry, he fixed some K, and he considered genus G to go to infinity. And then he said that the maximum size of a k-nice set is something like at most G to the K times log G, or something along these lines. And he applied some probabilistic approach to get this. Yes?
So in the last algorithm, you basically are trying to find the k-nice sets with mean height. How do you run this? Because if I just have a bad idea in my head, it's just exponential with h to the k, but is there something clever behind it?
There is something clever about it. Definitely, there are way too many points, especially if I take like k equal to 1891, so it is already a lot of points, and I multiply it by square root of 2k or something, which is something still around 60. Then I get a bunch of points, and I would like to consider all k-nice sets that sit there. But it is actually doable because, first of all, we are only interested in the endpoints at a particular level. And we can pre-compute what is the maximum number of points that we can include. And actually, we can always include everything between, because we know by this one of the results that I mentioned, points from the convex hull cannot break this crossing criterion. So there are actually a lot of values that we can pre-compute, and then what we can do, we can just simply go layer by layer to consider all possible choices of endpoints and see whether they impose two strict conditions for the number of remaining points in the remaining layers. So this is kind of a backtrack algorithm, and
but also low branching.
But of course, we need to run this algorithm for fixed choices of k and h. So there's quite a lot of things to be checked, but surprisingly, it's doable.
What's the largest value of K0 on this capital K0?
K0, you mean in which?
So in the main theorem statement, there was this exceptional set K0.
Oh, I mean, it is something below 891, of course. I think it was something around 600. I don't remember exactly, but it wasn't super high.
Curiosity.
Mm-hmm. So, but I think definitely above 1,000, everything goes as it should be. So it was just a matter of verification that there are like no exceptions.
And maybe I will just repeat what you said, but to make sure that I understand. In each of those exceptional cases, you do know the exact answer. It just doesn't have a nice description.
Yes, because this algorithm actually it determines the maximum size. Mm-hmm. So it actually finds k-nice sets and it gives as an output also the number of points inside.
Mm-hmm. Thanks. Is there any online question? Well, then, if it's not the case, thanks Bartek again for a nice talk.